So today we are talking about parabolas, which are the graphs of quadratic functions. And this is a great way for us to start our third week of Algebra 2 because we're really in the swing of things now. And this is one of the most important things that we need to learn in algebra. And why? Well, we've touched on this a couple of times before, but I just wanted to share with you, and this you can write down if you want to, or you don't have to. But Newton's universal law of gravitation says that the force of gravity is proportional to a gravitational constant, g. So this is a number just like 2 or pi or the square root of 7. This is just a number. It's a very specific number. And it's g times the product of the masses of the two objects and divided by the distance between them squared. So in other words, are you asking, is there a gravitational pull between me and my pen? Could I literally use the force to draw the pen to me? Yes. However, in this particular environment, the force of gravity between my hand and this pen is totally overwhelmed by something else. What is it overwhelmed by?
The Earth.
The Earth, yeah. So when we consider, if it's the mass of me and the mass of the pen and we're only a few inches apart, I'm going to be able to draw this to myself no problem.
Wait, what about when there's like no gravity? Then you can figure out floating in space.
If you are in space, you are creating a gravitational field. It's possible for there to be regions of space, in theory, where there is literally no gravity, but that would be because there's a total absence of mass or energy there. It would have to literally be completely vacant. If you are in space, you are creating the gravitational field. You will draw the little bits of stardust to you because you will be the most massive object in the vicinity. So that's why if suddenly you and your pencil were to be teleported to a region of deep space that really was very far away from any other massive or energetic object, yes, you could just stretch out your hand and your pencil would be drawn to your hand and you would feel like a Jedi. Now, this is a little bit of a tangent, apologies, but again, this is really, really important because this doesn't actually just work with massive objects. This also works with charged objects. So we have Coulomb's law, which is the force between two charged particles is proportional to a constant. So again, this is a number like pi or the square root of 2, or 6, times the charge of the first object times the charge of this second object divided by their distance squared. And now let me tell you something. When I first saw that in physics class, I was like, that is fishy. How can the interaction between two massive objects and between two charged particles be governed by almost exactly the same formula? Because magnets, for example, behave very differently from non-magnetized materials. Like I was like, this is fishy. And that's true because right now we're really questioning whether there is any such thing as mass and whether there is any such thing as gravity as we describe it here as a fundamental force. Is it actually just a side effect of the curvature of space-time? Is mass really just an expression of energy? So these are the exciting questions that are being answered by physicists right now. So if you're looking for a fascinating class to take in high school, I highly recommend physics. But what's really important to notice here is that whether we're talking about charged objects or we're talking about massive objects and we're talking about their interaction one to the other, the way that their position changes in space, the way they interact with each other, the way that they cause a force of attraction or repulsion, that behavior is always parabolic. The force doesn't weaken or strengthen linearly. In other words, let's just consider these two objects, these two pens. Okay? So let's just say they're pretty close to each other here, so there is actually a force of gravity attracting them. Now it's totally overwhelmed by the attraction from the Earth, which is much more massive. But if we imagine these two just being alone in space, and they're this far apart, and now we make them twice as far apart, is the force of gravity between them twice as weak, or some other magnitude of weak?
Is it squared? Or
Yes. So they're twice as far apart, so the force of attraction is 4 times as weak. 2 squared is 4. Let's say they're 3 times as far apart.
9.
Yeah, then they're 9. Then the force of attraction between them is 9 times as weak. So you can see how the force decays in this parabolic way, and that's going to have an influence on, it will have an influence on their motion. How quickly they're attracted, that kind of thing. Okay? And of course, when we think about it, when we step beyond this classroom or beyond this, this planet into our solar system or galaxy, this is why, what are the shapes that we see? We see circles and ellipses, we see parabolas and hyperbolas, we see motion that is all either parabolic or a cousin of a parabolic function. Right? Lily A., who is working on conic sections right now, is getting to know those cousins of the parabola. So you guys will get to do that in pre-calculus. We're going to focus on the parabola today. Okay? So in other words, this is extremely important. Parabolas are super, super important because the motions of all objects in our universe are dictated by parabolic forces, even if they're being pushed by an electric or magnetic charge, as opposed to a physical pull or physical push. So, let's take a look at this guy. All right, so who can tell me some vocabulary that relates to the graph of a parabola? What features does a parabola have? Or even if you don't know the vocabulary words, what are some features that you can see in the graph? Yes, Lily?
It has a vertex.
Yes, it has a vertex. In other words, it has an extreme point. It has, so if it's going the other direction, it has a peak. If it's going this way, it has a trough. Yes, Lily?
It has y-intercept and 2 x-intercepts.
That's right. So here we can see this guy does have a y-intercept. And importantly, it has 2 x-intercepts, which are also known as solutions. So if you're asked to solve a quadratic equation, you're looking for the intercepts. You're looking for the place that it crosses the x-axis. Like we talked about last week, if you were on a plane that is taking a parabolic path, you want to make sure it doesn't have any real solutions. In other words, you do not want it to intercept the ground. at least not at this angle. You want it to be coming in nice and shallow. I see your hands, Lily, but I'm going to see if anybody else notices. Was your hand up there, Gino? No?
Axis of symmetry.
Yes. So we have an axis of symmetry, okay? Now the circle feels very superior to the parabola because it is symmetrical in all directions. Okay, but the parabola does have one axis of symmetry. There's one line that basically, if you put a mirror right on this line, the reflection would look just like the other half of the graph. All right, and not surprisingly, these important features of the parabola are what give us the different equations of a parabola. So remembering with lines, remember we could do slope-intercept form, we could do two-point form, we could do point-slope form, we could do standard form. So we have lots of flavors of how to write the equation of a parabola. We got this first. We'll start with the vertex. Can anybody see numerically what the vertex actually is on this particular parabola? Like what its coordinates are? Yes, CC.
1, negative 4.
That's right. So in this case, our vertex is 1, negative 4. And in conic section parlance, the vertex of the parabola is indicated by HK. The vertex form of a parabola is y equals x minus h squared plus k. Let me double check and make sure that I've got that right. Yes, I do. And so for this particular parabola then, CC, if we are plugging in the h and k of this parabola, what is the equation? I'll let you know in this particular case, a is just 1. I can let you know that. But what's the rest of this equation going to be, CC, for this particular parabola?
I don't know.
Well, what is our h?
1.
Yeah. So this is going to be x minus 1. And what is our k?
Negative 4.
That's right. So this is the vertex form of this green parabola. So if you know the vertex of a parabola, you're very close to being able to write the full equation. I had to tell you guys that this was the a, that it was 1. You're not going to need to spend a lot of time on this in chapter 5.1, so you can just take that as a read. All right. So how about our x-intercepts? Who can tell me what the x-intercepts of this particular green parabola are? Where does it cross the x-axis? Yes. So this is crossing at -1 and 3. The intercept form of a parabola is y equals a x minus p times x minus q. And we indicate the intercepts are P and Q. So Taylor, again here our A is 1. What's our equation of this particular parabola going to be?
X minus, or actually x plus 1?
Yeah, why is it x plus 1?
Negative, minus negative is plus.
That's right, minus a negative is a positive. And
X minus 2?
x minus 3. All right, our last flavor of the equation of a parabola is the standard form, which is y equals ax squared plus bx plus c. And we can get to that. Here's where we're going to check to see, have we done our equations correctly? These two equations, y equals x plus 1 times x minus 3, and y equals x minus 1 squared minus 4. These should give us the same equation. Why should they give us the same equation if we reorganize them? Because they're describing the same parabola. So we'll be happy if we actually go ahead and FOIL this guy and we FOIL and simplify this guy. We should get the same equation. So let's check and see if we actually do. Now I'm saying the word FOIL. So let's go ahead and do that. We've got y equals x plus 1 times x minus 3. What do I mean when I say FOIL? Yes, Gio.
I think it's an acronym for like the order that you multiply each of the like numbers inside of the binomials. And so you multiply like the front two, so x and x. Multiply the two outside ones, so x and negative 3. You multiply the inside, so you multiply negative 1 and x. And you also multiply the last two, so you multiply 1 and negative 3.
Yes, first, outside, inside, last. So that's the acronym for FOIL. That's exactly right. And really what we're doing is we're doing just the very simplest matrix math. In a way, we're multiplying a 1 by 2 by a 2 by 1. So we're just doing the sum product. So we got to do some of that last week in chapter 4. Now we get to do a simple version of this here. All right, so when I multiply the first two, I get x squared. All right, help me out here, Gio. What do I get next?
X squared minus 3x.
That doesn't sound like Gio's voice.
Well, Gio didn't say
Okay.
anything.
Well, I'm thinking.
Let it think.
minus
It's not a
3x,
race. Yep.
plus x, and then minus 3. And then
Oh.
you can simplify it like and add that. X
That's right. We've got like terms here. So what is minus 3x plus x?
Negative 2x. And I guess you could, after this, I guess you could factor.
Well, but if we factor it, we're going to end up back with x plus 1 times x minus 3. So that's exactly, so factoring this here is basically reverse foiling. It's Lee-offing. No, it's not really Lee-offing. That acronym wouldn't make any sense in context, but I like, that was a joke just from me apparently. Okay. So I'm going to throw this one to you, Merlin. Is x minus 1 squared just x squared plus 1? No, because why? What do I have to do here?
I don't know. Distribute the 1? Or...
Oh yeah, well, if we distribute
Yeah.
the 1, multiplying by 1 is just an identity. So we end up with x minus 1 squared. But how do we actually compute x minus 1 squared? I will say this is the place where I most frequently see a mistake. I see somebody go, oh, well, x squared is x squared, and negative 1 squared is plus 1. This is the most common mistake I see, but that is a mistake. What should I be doing here?
I would have done that.
Oh, well, see, okay, all right. So I didn't mean to throw you under the bus on this one, Merlin. It wasn't meant to be a trick question. Okay, yes, Cece?
You had to foil that one too.
We have to FOIL this one too. Because remember, x minus 1 squared is just x minus 1 times x minus 1. So we're going to end up with an x term. If we skip this part, then we're going to, if we skip that part, then we're going to end up with a missing our x term. All right. So, but let's go ahead and I'll throw it back to you, Merlin. Here's your chance at redemption. Let's actually go ahead and FOIL this. What do I get when I FOIL x minus 1 times x minus 1?
2x. For first.
Well, 2x?
That's fair. That's fair first.
Yep. There is an x and a 2. Yes, good. Okay.
And then negative x.
Yes.
Negative x.
Yes.
Plus 1.
Plus 1. Very good. Okay. So now we can combine like terms. When we combine x terms, what's minus x minus another x?
Minus 2x.
And what's plus 1 minus 4?
Minus 3.
And now am I happy or am I sad?
Happy.
Well, I am happy, Lily.
Happy.
But why what's determining my
Because they're the same.
That's right. And we want them to match because these two equations are of the exact same parabola. Yeah. Yes. And so we can see here then the standard form of this parabola is y equals x squared minus 2x minus 3. There's one final piece here. What is the equation of the axis of symmetry for this particular parabola, Gino? That's right, x equals 1. Okay, now as it turns out, when I'm looking here at the vertex, my x coordinate is 1, and my axis of symmetry is x equals 1. Is that a coincidence, or should we expect that every time? Who can explain? Let me repeat the question. I can see on the vertex of our parabola here that the x coordinate is 1. And I'm also seeing that our axis of symmetry is x equals 1. Is that a coincidence, or should we expect it? Yes, Lily.
We should expect it because the vertex is always on the axis of symmetry, and therefore the x coordinate should be the same.
That's exactly right. Is it possible to draw a parabola where the vertex is not on the axis of symmetry,
No.
in other words?
No, because either you've got a wrong vertex or a wrong axis of symmetry.
That would be a very bloopish parabola, and then it would not be symmetrical. If the one extreme point was sticking over here or sticking over here somewhere, someplace else, then all of a sudden the parabola isn't symmetrical. So yeah, so the vertex is always going to be on the axis of symmetry. All right, go ahead and look again at page 249. And we've got a green box there. And it tells us a little bit more, because when we look at the equation like this, do we have any clues about what the vertex or the intercepts are? Are there any direct links between standard form and any of these important features of the parabola?
Well, you have the y-intercept, but
We do. In this case, I will say, though, it turns out that is simply coincidence. So in this case, we've got this 3. But here we've actually got a negative 3. So again, we don't really have a direct link between the standard form of a parabola and what the graph looks like. Let's go ahead and try out this rule in this green box on page 249. From this equation, how could I calculate what the axis of symmetry is. You've been our axis of symmetry person today, Gino, so I'm going to throw this one to you again. Using just this equation in the standard form, how do I calculate what the axis of symmetry is?
For x, it's like negative b over 2a, so it'd be negative, I guess.
Yep.
And then over 1, or 2 times 1.
2 times 1. And negative negative 2 is positive 2, so we have 2 over 2, which equals
1.
1. Okay, so now I know that the axis of symmetry is x equals 1. All right, Taylor, if I know that the axis of symmetry is x equals 1, what's the x coordinate of the vertex?
One.
Yes, because the x coordinate is always going to be on the axis of symmetry.
My brain just shut off.
Yeah, but I saw it whir back to life though. It's like I can hear the fan on the computer coming on. It's like, can't put it back to life. Okay, if x equals 1 is the equation of our axis of symmetry, and we know the x coordinate, therefore, ergo, ipso facto, the x coordinate has to be 1. How do we find the y coordinate? I see your hands, Lily. I know you already know this one, so I'm gonna give Taylor a minute.
Do you plug it in?
That's right, we plug it in. So we're gonna have y equals 1 squared minus 2 times 1 minus 3. So we've got 1 minus 2 minus 3. Oh, I kind of like the way that looks. And Taylor, what is 1 minus 2 minus 3?
Negative 4.
I saw possibly some some crutching on what we know the answer has to be, but yes, 1 minus 2 is negative 1, minus 3 is negative 4. And so we're very happy because we've come back and we've found the coordinates of the vertex, and we have found the axis of symmetry from the equation in standard form. One final thing. How do we know, just looking at the equation of a parabola, whether it's going to be a smile, an open up, or a frown, an open down?
Something to do with negatives.
The
X.
leading coefficient.
There we go. Yes, that's right. I'm seeing pointing. I'm hearing x's. I'm hearing leading coefficient. That's right. So if we instead had the equation y equals negative x squared, plus 7x, plus 18, all of this is all looking really positive where this was looking negative, but it doesn't matter. It's just the leading coefficient. If the leading coefficient is negative, we have a frown. If it's positive, we have a smile. All right, there's a few more nuggets in here about graphs of quadratic equations, graphs of parabolas, how to go back and forth between the equation and the graph, and all that jazz. But this should be sufficient information to get started on chapter 5, if you haven't done so already. Does anybody have any questions about what we have up here on the board right now? All right. In that case, go forth bravely, mathematicians.